Hi everyone, I'm going to present our works on image-based pose estimation and shape reconstruction for robot manipulators and soft continuum robot via differentiable rendering. The robot state estimation has been a challenging task for the robotic community. To estimate the pose of articulated robot, various calibration methods using markers and key point detection have been proposed, followed by the forward kinematics to calculate each joint state. With the development of soft robot for different applications in recent years, the shape estimation has become crucial for robot control. Researchers have investigated sensing techniques based on magnetic and optical sensors, as well as modeling approaches using curvature shapes and FEM. However, these approaches have several limitations. The use of markers require modification of the robot, and many methods require offline calibration. Sensors may present measurement errors for soft robots, and the modeling approaches may not be accurate enough, requiring complex computation. In this presentation, I will introduce our approach for estimating the state of robots by only rendering them into images. Our approach for robot state estimation involves formulating the problem as an optimization-based approach. We calculate the loss term by comparing the rendered robot image to the binarized robot mask image from captured real data. The aim is to optimize the robot state parameters represented by theta. We can take different forms for articulated and soft robots. For soft robots, we represent the robot states using a Bezier curve model, where the radius along the curve is used to represent the surface mesh variation. Using these parameters, we can reconstruct the mesh or rendering it into an image, and then calculate the loss by comparing it to the binarized mask. It's worth noting that our method is differentiable. The forward path is indicated by the blue arrow, while the green arrows represent the backward path for gradient calculation. To represent the articulated robot, we use the camera-to-robot pose transformation as the robot states. For each link of the robot, we use cylinder-shaped primitive by adding offset values to each mesh vertex. The forward kinematics is then applied to reconstruct a chain of mesh for rendering. Same with the soft robots. We calculate the loss by comparing the rendered image to the binarized mask. The parameters can be optimized through optimization. To summarize our proposed approach, we have divided our algorithm into 4 steps. The initial step involves mesh reconstruction using the given robot state parameters, followed by rendering the mesh into an image. The last 2 steps use gradient-based optimization with loss computation. In practice, the mask loss will have no informative gradient when there is no overlap between the rendered image and the mask. To address this issue, we use 3 key points along the curve and the end effect point as additional losses for the soft robot. For the rigid robot, we use a distance field in combination with the appearance loss. These losses help get optimization to avoid local minima. Here, we provide an example of pose estimation for the box robot arm with a binarized robot mask and a random initialization of the robot pose, as well as the shape mesh primitive offsets. The optimization converges quickly. In our video, we compared the performance of different losses for soft robots. When using only mask loss, the tape can't be properly converged. However, adding endpoint loss improves the performance. Using 4 key points represented in the interior shape being well converged. We also reconstructed the whole soft robot trajectory frame by frame. The result is also rendered with OpenGL. We can conclude that by combining these losses, we achieve a more robust convergence for robot pose estimation. Our work highlights the contribution of performing state estimation through a single image for both rigid and soft robots. We have formulated the problem using a unified mouse modeling approach with shape primitive, and the differentiability of our approach allows for optimization with readily available gradient. Additionally, our proposed novel loss function have been shown to improve convergence. Thank you for your listening.